Now let's invite our next speaker, my colleague T.R. Govindarajan. What? Kriya University. And
Well,
IMSC. Okay.
IMSC also.
Okay.
Thank you. Okay, thank you very much. Thanks the organizers, director, secretary, everyone for inviting me. Krishna also. I'm very happy to be here because as Murthy mentioned, I'm grant student, and I also mentioned yesterday of Professor Alladi Ramakrishnan. And as I mentioned earlier, yesterday, let me remind you that we have a great legacy. We go back to Newton himself. So with that pride, I will try to give something in this talk. This talk I have actually given at different places, which I have listed, but most of them were 1 hour talks. So I had to cut down to tell. Secondly, the audience was also much more high energy physics group, but here the audience is going to be is mixed. So I've made it to the best possibility, best thing about myself to make it understandable for everyone. Okay, I don't want to lose the audience right at the beginning. So with that, I'm going to give this thing. So the title is strange, light as dark. So I have to explain what is meant by the two terms. And after doing these explanations, the first 4 things are going to be the basic physics which is there. And I'm going to make last 5 minutes kind of provocative remarks, which probably all of you may want to attack me. Okay, let's go with that. Okay, so what is dark is the first slide. Our universe consists of matter, dark matter and dark energy. And the matter which we know, which we see in the stars, galaxies, etc., is only 5%. Very little we see. Now, if you take a galaxy like Milky Way, which is there, 80% of that is dark matter, what we call dark matter. Why is it we need? I'll tell now. Most of it we don't see, okay? But it is needed because even the structure of galaxy is there as stable object, to some extent stable object, because of the dark matter. And the last one, 75% is a dark energy, because there seems to be an accelerated expansion of the universe itself, which is played by this kind of energy, which I'm not going to touch upon. So my part is essentially that 5% and 20%. Now, why is it we have to talk about dark matter? The idea is very simple. Now, if you take the solar system, sun is there, various planets are there. Kepler told us the farther the planet is, it is going to go slowly. The velocity will be less. That's what Kepler's laws are telling. Universal law of gravitation of Newton also produces that. Same thing is true in general relativity also. So we don't have to worry about it. So general relativity or Newton's will be somewhat similar. But when you see the galaxy as a whole, Milky Way for example, there is at the center, there is a huge monster called the black hole, supermassive black hole, which is at the center, and all the stars and other things go around it, like our planetary system here. So what you expect is the stars far away from that should go at a lower speed. The stars which are closer to that will go at a higher speed. That's what you expect. And you expect a curve like A for the stars far away from it. But unfortunately, when you see it, it doesn't happen. What is there is B, the curve B. So the stars far away from the center also go at very high speed. That is what is there. And this was a puzzle. And the puzzle was, there are so many other matter which we do not see. They are playing a gravitational role, which is called dark matter. We call it dark matter. And that is what is affecting the whole thing. And such a thing is needed even for the stability of holding the galaxy together. Okay. So that is one part about what is dark matter. Now, dark matter Nobel Prize, it was proposed earlier and it has been verified by various other experiments. like what they call uh, the gravitational lensing, and also bullet clusters, various things which are there. There are also dwarf galaxies, which I'm going to worry about later. It has been verified, and there are people are happy with that. In the sense, we have to explain it in some way. So this prize was given to Peebles in 2019 or so, 18. And because the prize was given to James Peebles, but it was discovered by Vera Rubin. And there is also a bias against women controversy is also going on. And this is a background to this story. Okay, so the galaxy, this is about the dark matter. Galaxy clusters, mass distributions, we measure it. We can actually measure how much is it in couple of independent ways. Radial velocities within the clusters, X-rays from the cluster spectrum and flux give the detailed estimate of the temperature, pressure, etc., etc. So at this point, the existence of dark matter in the Milky Way galaxy or any other galaxies is typically of the order of 5:1. So most of it is only dark matter. So the dark matter and usual matter are matter in the real sense of the thing. It's not like dark energy. They do not evolve in the same way after Big Bang. They don't evolve in the same way because dark matter evolves in a different way from the regular matter. And because dark matter is not supposed to interact, because the whole idea is it doesn't interact. Otherwise, if it produces electromagnetic radiation, we would have seen it. So since we have not seen it, they don't evolve in the same way, and we have to understand it. And even the so-called cosmic microwave background thing also will show some differences. And the dark matter is crucial for structure formation itself. And several candidates have been proposed. I'm not going to talk about that. In fact, in the last lecture also some candidates were mentioned, sterile neutrinos, etc. And many of them, in fact, there is no accepted candidate as of now. We don't have. There are people are searching for it. Okay. So the sterile neutrinos, various things are there. I'm going to be bothered about. There are people who say even Newton's theory of gravity is wrong. General relativity is wrong. We have to modify the gravity theory itself when acceleration is very, very tiny, which is called modified Newtonian gravity. So MOND is one of them. Now I'm not going to be bothered about many of these things because I'm going to focus on what is it I have to say. And that is a novel proposal I'm trying to make. I've been involved in and doing more calculations. So that called fuzzy dark matter is a model which suggests it is not like neutrinos, sterile neutrinos, etc., where the mass is of maybe of the order of 0.1 electron volt, few electron volts, etc., etc. It is really, really tiny mass, extremely tiny mass. Mass can be zero, close to zero, but not zero. This is the kind of a thing which is 10 to the power minus 20 electron volt. For a comparison, electron has a mass of something like 0.5 million electron volt. 0.5 million electron volt, which is one of the lowest ones, like compared to that, it is 10 to the power minus 20. This is basically the idea. So that is as far as what is dark is concerned. Now what is light? The light is electromagnetic radiation, which is Maxwell's equations, which I have written down here for your benefit. And these are well-known equations, so I'm not going to repeat it. So we have the equations given in the form of vector potential A mu and scalar potential phi, okay? And the last equation 1 is essentially that statement. We have a current, we have charges, and the charges move the current. So these two are the things which create my electric field and magnetic field. If you have a charge, there is an electric field around it. If the charge is moving, it creates a magnetic field around it. This is what was done by Faraday and others about more than 100 years back. Okay, so I gave a talk in DIAS, what is called Dublin Institute of Advanced Studies. The mass of this particle, quanta of electromagnetic radiation, was supposed to be, it is whatever that equation gives, there is no mass. So mass is zero, which means it is so-called rest mass. You cannot bring it to rest. That's what is the whole idea. So this is the thing, should it be massless? That is the talk I gave. And very surprisingly, I found out Erwin Schrödinger gave a similar work About 1955, he asked the question, must the photon mass be zero? That is the reference for that. And he was not interested in the kind of question I am asking, but he posed this question, should it be zero or not zero? Like the way Murthy went about, should it be zero or not zero? Now the problem with this photon or light is, if it is zero, it has 2 degrees of freedom, as Balchandran was mentioning, it is the helicity. 2 degrees of freedom. The photon is going in this direction. Perpendicular to that, a plane, there are 2 degrees of freedom. That's what they have. Electric field is only in that perpendicular thing, which is there, 2 degrees of freedom, which we call it as a right-handed polarization, left-handed polarization, even in the earlier classical electromagnetic theory. Now, what was done was, in the last century, people were doing what is called black body radiation. What they did was, you take a box, find the standing modes in that. Just take a string and then let it oscillate. What are the modes in it? Find out all the energies associated with that and compute the energies, and then since you don't know anything, you just integrate it. And the energy density is what I have given here on the left hand side, here, and that factor 2 is very crucial. It is assuming it has 2 degrees of freedom, they multiply it by the factor of 2, because they are not interacting, as it was mentioned earlier, they are not interacting, they multiply by the factor of 2, and that factor of 2, when you do this integration, will give me the total energy, which is going to be this formula, and the sigma which is there is a measured quantity. You experimentally measure what it is, and it is what is known as Stefan's constant, and with the factor of 2, you get a number for sigma which is agreeing with the experiment. So the whole idea is we should multiply by a factor of 2. Now this gives rise to certain problems. The problem is between Bose and Einstein. So Bose, actually I will come to the conflict, should we multiply by 3 to account for the additional longitudinal degree of freedom? Is there one more degree of freedom along that, or is it 0? That is the question. And answer was given by Schrodinger himself. He said, if the vector potential A mu is coupled to J mu, which is conserved, d mu J mu is 0. If it is conserved current, then the longitudinal part, even though it is there, it interacts with matter very, very little. In fact, 0 interaction. So what happens is, it's only transverse part which is interacting. Longitudinal fellows don't even interact with the matter part of it. So what he does is, you should not multiply by a factor of 3, you should multiply only by 2, because in a box which is there, it is the electromagnetic radiation which goes and hits the wall, and the electrons are there on the wall, which interacts and then reflects it. That's what is happening. So you should multiply only by a factor of 2. This is his conclusion, and he went ahead with that. Now this is a famous remark which closely related to this thing. Even if we find in nature, at the all experimental level, it is found to be 0. We don't find 0. We will find it so small that you can't even measure it. That's what is happening. The limiting case is realized. Limiting case is realized. We should still feel the urge to adumbrate a theory which agrees with the experience of approaching that limit. This is very crucial. How do I know it is 0 or very tiny? How do I make the difference? That is what is the thing. So only a small change in the S matrix contribution, these are calculations like the way these people were doing, if m gamma is small. So what he did, he went ahead and found out, is there a limit on the mass of the photon? Simple calculation. And the equation number 2 is the equation for the vector potential, which will tell me what is the mass of the photon. Because vector potential is related to the magnetic field, and I know the magnetic field on the surface of the earth. I can go and find out what is the mass limit it will give me. So the answer is in the equation number 4. If the mass is 0, one value. If the mass is not 0, another value. That extra which is there for mass not equal to 0 is related to when it is equal to 0 is that equation number 4. And that r which is appearing there is the radius of the earth. It is the radius of the earth. So what he did was, he knew very interestingly by 1925 itself, the magnetic field on the surface of the earth in thousands of places were known. So he took the magnetic fields expected from there and compared it and got a limit on the mass of the photon. And the answer is it should be less than 10 to the power minus 47 grams. This is a very unit is very small. Now the actual, I prefer being a physicist, high energy physics person, to give it in terms of electron volt. We don't talk about mass in grams, we talk about the mc square. Okay, multiply c square and then get the electron volt result. It should be less than 10 to the power minus 16 electron volt. Okay, this is what Schrodinger got. And the thing is, the current value is 10 to the power minus 18 electron volt. In fact, Schrodinger did a very good job with the data which was available. Now the data has improved. If you take the particle data book as of now, it tells you the mass is less than 10 to the power minus 18 electron volt. It's less than that. It doesn't say it is 0. It can be 0 still. Okay, that is what is the thing. Now, if the mass is not 0, different frequencies of light, there are X-rays are coming, ultraviolet ray is coming, gamma rays are coming, various frequencies will have different velocities, and you can find out time of arrival from a star. What is the thing? From the speed, you can try to find out the mass, okay, limit. That gives a very, very poor limit. In fact, it is 10 to the power minus 42 grams. That's what the limit is giving. So, Schrodinger's calculation was very good proposal, and that is an accepted fact now. Okay. How do I give the mass? So, you add to the Maxwell's equation which you have, what is the extra term which you will have? M square times A mu, which is added to the what is called the Procca equation. But the problem with the Procca equation is, with mass term, there are two problems. One is, it has 3 degrees of freedom as we mentioned, whereas in the massless limit, it is 2 degrees of freedom. There is a discontinuity seems to be there. Secondly, with the mass term, it breaks gauge invariance. Okay, it breaks A mu square is not gauge invariant. A mu going to A mu plus d mu chi will change the A mu square value. F mu nu will not change, but this will change. So, gauge invariance is lost, and gauge invariance is more or less a paradigm on which our whole standard model is based on. So, we would like to have gauge invariance. The interesting thing is Stuckelberg, an extraordinary physicist who is not recognized, in my opinion, to the extent he deserves. In fact, he discovered renormalization group before all these people discovered. He also discovered Feynman's, the perturbative QED, the results were discovered by him, which was acknowledged by Feynman himself. In fact, he has mentioned it in one of the things. So, this is a kind of a person, and he solved this problem. How did he solve the problem? Instead of A mu square, he introduced one more field phi, and he wrote this combination, and that combination is gauge invariant. That combination is gauge invariant. Whatever transformation A mu goes, this d mu phi cancels it, and the theory is gauge invariant, and there is no problem, it has mass, everything is fine with this theory. Now you can say this is more or less a precursor to Higgs mechanism, which was discovered some 10 years or 15 years after Stuckelberg gave. And this is the thing, you can introduce Higgs mechanism also to give mass to the photon and make the value of the Higgs field very high mass, and so that only the phase which is here is the only thing plays the role in our thing. It is a Stuckelberg theory. So, as far as I am concerned, there is a Stuckelberg field which is phi, A mu field is there which is transverse, and these two are the things which are there. Now, what now? Where do I stand with the dark matter? As I said, the Stuckelberg field, which is the longitudinal component, does not interact with matter. Like today, Jagannathan was asking something doesn't interact with matter. Can it be dark matter? Now, there are problems with his proposal, but there are no problems with this proposal. So, it does interact with very, very little. There is no interaction in a practical sense. So, I say the Compton wavelength is h by mc. I am using the units h bar is 1, c is 1. In that length scale, there is no interaction between them. So, the question is, it has energy, it has mass, and it can gravitate. And can it contribute to the dark matter? That is the question. And now it is really amusing to call, because this is part of light. The light, and you call it dark. That's where my title is coming from, light as dark. But it's also one more twist to the story. because light has two meaning. One is electromagnetic radiation. Light is very light. It's very tiny mass. Okay. So my mass is also 10 power minus say 20 electron volt, which is tiny. So this is basically the idea. This is the proposal. Now the problem is, if the mass of the candidate is too small, like the way I am talking about, even neutrinos, we all know they travel with very high speed. It's as close to the velocity of light as you can expect. It might be 0.99 c or 0.999 c. It travels so fast that it is. So what will happen is, after the Big Bang, if it doesn't interact, it will simply escape even in the formation. So it cannot help. It should somehow stay there together and make the possibility of a galaxy and other things in the later stage. When the nucleosynthesis and other things happen, at that stage it should be there. So it is important, the mass should not be tiny in a conventional sense. But that is where our Bose and Einstein come back again. And again related to the question of quantum statistics, which Murthy was raising, and I am going to answer some of the points which I mentioned here. So what he said was, the problem is these particles are bosons. The bosons tend to clump together. There is no problem. In fact, if you take a collection of this thing, given no other thing, they all will go to the same room. They will have the lowest possible energy if it is there. But if the temperature is there, it will go up. But if the temperature is not there, zero temperature, all of them will go to the ground floor. It is not like fermion, what he was worried about. Even if the temperature is not there, the fermion will try to go above, first floor. One will be there, second one will be on the first floor. That's what will happen. Bosons don't do that. They try to go together, and that was realized by Einstein, which is called Bose-Einstein condensate. So this is basically the idea. They form a Bose-Einstein condensate. Very, very this thing. And that is related to real physics also now. So now, since I gave this talk in Bose, S.N. Bose Institute, dedicated to Bose, I also realized this is the 100th year of, like our father, 1924 was the time when Bose gave that paper. And that's why it is called 100th year of Bose thing. They are going to have 1 year of celebration. And that is the thing. Okay. So what is the crucial point? Bose-Einstein condensate. Let us ignore all the things which are there. The crucial thing is, there is a critical temperature below which the condensate will be formed, above which the condensate will not be formed. The critical temperature, as I have written down, has 1 by m to the power 1/3 at the bottom. Okay. Now, Bose-Einstein condensate has been obtained in the lab, but they have obtained with rubidium gas. Rubidium gas has 86 AMU or 86 protons or neutrons, etc. Combination of them. So it is, each one is 1 giga electron volt, 10 power 9 electron volts. So 86 into 10 power 9 electron volts, the temperature at which they form the critical temperature turns out to be nanokelvin. You have to go to your temperature at not even at minus 273 degrees centigrade, you have to go to nanokelvin at that thing. Very, very tiny temperature. But now our masses of the order 10 power minus 20, minus 22, I don't know, but it is less than that. So if there is a possibility, they can be formed at very high temperature. And it turns out it can be formed at Big Bang temperature itself, close to that, close to that. So this is the thing, then they can form a condensate. After forming a condensate, the condensate formation is a force by which this whole thing is not, you cannot talk about them as collection of particles. Like for example, if you have a collection of particles which is making your tumbler of water, you don't talk about it as water molecules. We talk about it as water fluid. Now we have a fluid of this kind of particles. We should talk about them as fluid, okay? Something like a superfluid. So this is the kind of a thing, and this is a famous graph which is always given after the Big Bang, what happened, etc., etc. And close to 10 to the power minus 15 seconds. Mark the word, 10 power minus 15 seconds after this thing, this kind of thing should have been formed. Close to that. I am working on the calculations. Okay. So estimating this, there are several critical temperatures I have worked out. We have not come to this thing. There is possibility. We don't have a parameter. We don't know what is M gamma. depending on the temperature will change, and that's what I have written down. And we can do some calculations with what is called FRW metric, etc., and find out how the evolution takes place. I will not describe those things because it will go into little technical about it. And what people do is this kind of condensate can form in the galaxy. There is a half radius for that, and there is a density at the center, okay, and that was worked out in the thing. But the crucial thing is, what are the proofs? Where are the evidences? That is the question. Now the question is, around, for example, Milky Way galaxy itself, there are about 40 dwarf galaxies. Milky Way galaxy has about trillion stars are there, 10 to the power 10 solar masses, something like 10 power 10 suns are there. That is what is the thing. But actual mass of the Milky Way galaxy is 10 power 12. So huge, 100 times more. Okay, that is what is there. There are dwarf galaxies which are there, which we don't see. We don't see it. And most of it is only dwarf, many of these things. And as per the estimation, there should be at least 200, numerical simulation has said 200, or the order of 200 dwarf galaxies should be there. And I'll tell you what are the dwarf galaxies, but we have found only 40. The rest of them are faint. They don't even see even by that. So this is what is the thing. So I will not explain this part, which is about the half radius and density of halo. So this is basically the idea, and let me try to the dwarf galaxies itself. Now the dwarf galaxies, the size of the dwarf galaxy, see Milky Way is millions of light years across. Dwarf galaxies can have something like 1000 light years, something like 500 light years, something like 10,000 light years. It's not millions of light years. How many stars are there? There can be of the order of 1000, maybe 5000, that kind of thing. Whereas in Milky Way itself, trillion suns, trillion stars are there. Compared to that, that's why they are called dwarf galaxies. But they also have dark matter. Each of these dwarf galaxies also have a dark matter. And most of it is only dark matter. In fact, the proportion of dark matter in a dwarf galaxy is more than the proportion of dark matter in the Milky Way itself. So this is the kind of a thing. So I have a prediction. What is the prediction? The prediction is whatever is the mass of the dark matter candidate, the Compton wavelength, which is going to tell me what is the size of the condensate, what is the size of the condensate acting as a fluid together, that it cannot be less than that. Okay, you cannot have a dwarf galaxy which is less than that. I checked all the data. The lowest is what is called Segu or something like that, and that has a diameter of about 250 light years or something. The lowest, in my calculations are correct, it cannot be less than 150 light years. But we don't know the mass. It depends on the mass of the candidate which we are going to tell. Okay, we can do better estimates also, which I am involved. There is a person by name Ryuto who has worked with Maxwell-Proca equation. He found out what is the energy momentum tensor, and from the energy momentum tensor with massless photon extra longitudinal component, there is extra energy and momentum, and that extra energy momentum gives you extra pressure. He finds that extra pressure due to that thing in a Compton length scales, that actually is, there is a repulsive thing which is there, which is coming from there. That is what is the thing, which is actually the scale of the longitudinal photons. Okay, now coming to Murthy's thing, there is a theorem. The theorem is due to Landau and Yang. Okay, Landau-Yang theorem. A massive spin-1 particle cannot decay to two massless photons. It is very simple, as Bal was mentioning. It is nothing to do with your Lagrange, nothing to do with your Feynman diagram, nothing to do with your action, nothing. It's only pure kinematics of representation, group theory. It is only group theory. If I take massless photon representation, which is a massless photon vector particle, take product of two representations, does it contain a massive spin-1 particle representation? That's a question, as simple as that. Product of two representations will give various, it's no longer irreducible, it will be reducible. Find out the representation content of that, as simple as that. And the important thing is the two massless photons should be bosons. you have to apply both statistics. That is also crucial. The theorem simply says you cannot write an amplitude involving a massive spin 1 particle going to 2 massless photons. So this is the famous theorem, which was due to Landau and Young, given in 1940s, late 40s. And but only thing is, if the mass photon has mass, there's a tiny mass, there is an extra component which is coming. So it can violate the theorem, which is going to be of the order of m gamma square. As he was writing, the extra terms are going to contribute for this, and that is a kind of a thing. So, but only thing is, doing experiments at that level is going to be very, very, very difficult. Okay. Now, I have made a generalization which is related to the question which he is doing. 5 minutes? Sorry. I have done, because it is related to this thing, I wanted to mention about that. So, the thing is, I can do a supersymmetric generalization. You can ask a massive spin 1 particle representation, can it decay to massless spin 1, the thing. In that case, it is actually photon and photino, and the vector particle is also there. Can it, a particle go to 2 photinos, which are Majorana particles, which you wanted? The supersymmetric grants me that it is not possible for a spin 1 particle to go to massless photinos. I'll come to that. But they are massive. They are massive. No, I'm coming to that. I'm talking massless. Okay, in the limit of mass going to 0, it has to go to 0. That's what I'm telling. In the limit. So this is basically the idea. I asked Balachandran about it. He said he has actually proved a theorem. A massive spin 1 particle cannot go to 2 massless spin 1. Spin half particles is what coming from simply representation theory, which he told me, but my supersymmetry will guarantee that to that extent. So I'm going to stop here, and various things are there with respect to pulsar timing array, which I promised to Manjari. So now there are new experiments which tell you that there is a hum of the gravitational wave coming from mergers which happen close to the Big Bang after the thing much later. At the earliest big thing, galaxies merger, and it is there, and it is seen through the pulsar which are there in our galaxy itself, and that also gives a very nice new limit. The average distances between pulsars is, if you relate it to Compton wavelength, it says the mass of the dark matter candidate cannot be less than 10 power minus 24 electron volt. This is the kind of estimate which is made. Now I have two limits. One is it has to be less than 10 power minus 18. If my candidate is correct, it has to be greater than 10 power minus 24, and it may fix the kind of a thing as a measurable thing, and I'll have. So I'm going to stop here, and I will not talk about the provocative statements about ether, etc., etc. I wanted to say, but I don't have time. Sorry. Thank you. Thank you very much. I have to make sure Krishna has taken the photograph. Thank you.